I want to talk just a little bit more about how an MRI works. And of course, MRI stands for magnetic resonance imaging. In order to talk about that, though, I do want to spend just a minute first and talk about just how regular photography works. So how does regular photography work? Well, regular photography works by, light from the sun or something like that, or maybe a light bulb, bounces off of an object and it hits some film, or that's old school. In your cell phone, you have a CCD, a charge-coupled device. It's just an electronic device that records the fact that some light hit on a specific location. Okay, so it hits some film or a computer chip in your camera somehow, and it creates an image. So again, it is light that bounced off of an object, and then it created an image on that film. Let's compare that with the way that a X-ray works, for example. So if instead of this regular photography here, we were working with an X-ray, well, it's similar in that we still have a piece of film over here, but it's a little bit different in that I now shine my light from over here, and it's not exactly light, it's X-ray, it's some X-ray source. X-rays turn out to be produced by rapidly accelerating electrons. So you need some sort of a fast-moving electron, and then you stop it really quick, and it will emit an X-ray. At any rate, these X-rays come through here, and instead of bouncing off of the object and into some film or something like that, they actually pass through the object. Now, X-rays are very high energy. It's just kind of like light. It's electromagnetic radiation. More on that in the next chapter. But they're very high energy. X-rays have so much energy that they pass right through the soft tissues of your skin, but they get stopped by your bones. So what happens is these X-rays hit your body. If they hit some soft tissue, they go on through and expose the film. And if they hit a bone or something like that, then they get stopped. And so you're kind of seeing an image of the shadow of your bones. And I won't draw all the leg bones on my picture. But at any rate, you just see the hard things. Why? Because it's kind of a shadow. So it's similar to regular photography, but a little bit different. It turns out an MRI is much like this. In this case, we're getting an image of where the X-rays were absorbed, right? So we're able to get an image of the inside of the body by seeing where these X-rays got absorbed. Now, MRI works in a similar way to this, but it's a little bit more sophisticated, and an MRI can give you some spatial information that an X-ray can't. An MRI, however, uses magnetic resonance imaging to create a three-dimensional image of the body. How does that work? Well, the key to the technique is the magnetic nature of atoms. Specifically, nuclei of atoms have a magnetic field all of their own. And so, the magnetic field of the nucleus, they act like just a magnet. I mean, a nucleus acts like a magnet. And that magnet of the nucleus of an atom can interact with magnetic fields that might surround the space where those nuclei exist. So, what an MRI does is it interacts specifically with hydrogen nuclei. And of course, hydrogen is number 1 on the periodic table. So a hydrogen nucleus it's just a proton. Now, an external magnetic field will exert a torque on a nucleus, but it will exert a different torque on different types of nuclei. So again, an MRI is able to image hydrogen nuclei. Probably scientists could make it so that it image different nuclei, but since hydrogen is all over in our bodies, since we have a ton of water in our bodies, then it makes a nice, there's a lot of it in our body. Okay, so here's a person in an MRI machine. And an MRI machine, and maybe if you've ever seen one, they have this huge donut-shaped structure, often. And what's in there is a coil of wire, which carries a very, very, very large current. In fact, it carries such a large current that the heating bills would be enormous if this were made out of regular wire. So you know what? This is made out of superconducting wire. It turns out that certain materials, when you get really close to absolute zero, they can conduct electricity with zero resistance. Not just a little bit. I mean, we're talking zero, literally zero resistance. And we know that it's resistance that creates heating in wires. So a wire with no resistance creates no heating. So it's cheaper for them to keep these coils near absolute zero than it is to pay the heating bill to disperse the heat that would be generated if these were non-superconducting coils. That's pretty crazy. So they run a huge current through this coil, which of course creates a magnetic field. Now that magnetic field is not the same over this entire person's body. We know that as I get farther from that coil, the magnetic field decreases. And so we could kind of make a plot here of magnetic field strength, and this would just be, position along this person's body. And without getting too worked up about exactly what the shape of that is, it's real strong when I'm close to the coil, and it falls off, and it decreases the farther along the person's body I get. In other words, the magnetic field strength of the external field, which is the field created by the coil, is stronger at the person's head than it is at the person's feet. Now, we're going to choose to interact with just the protons in hydrogen nuclei, as I have stated. And so each one of these hydrogen atoms can either have its magnetic field with the direction of the external magnetic field or opposed to the direction of the magnetic field. And it turns out that those two states have very different energies. So here we see an energy diagram, and this would be the energy of a proton if its magnetic field is aligned opposite to the external field. And it's a lower energy state if the proton has its field aligned with the external magnetic field. Now, a key point here is that the energy difference depends on the magnetic field of the proton and the strength of the external magnetic field, which means that the delta E for some point right here would be greater than the delta E for some point down here. So delta E1 would be greater than delta E2. Well, what does that have to do with making an image? Well, what we do is we've got this person in this magnetic field here. Now what we do is we send in a probe field, what's called a probe field. And so this is just electromagnetic radiation that I'm going to send in. And by tuning the frequency of that electromagnetic radiation, I can tune the energy of that electromagnetic radiation. And it will get absorbed at different places in the body depending on the energy difference between opposed and aligned. So if I tune this to have some delta E, let's call it delta E3, so this has some energy corresponding to some point in between here, then this is where that light will be absorbed. So it will be absorbed by protons at this location in the person's body. And so we know that we're making an image of exactly this person's, the location right here in this person's body. So it's just like an X-ray where we're kind of getting a shadow of the person's body. But what we're getting is we're getting a shadow of the hydrogen atoms, and we can figure out exactly, by tuning the frequency of this incoming field, we can adjust it to make it so that we're getting an image of the protons in the hydrogen nuclei in the person's body at different places. Now, scientists know that the heart has, that heart tissue, for example, has a different water content than bone tissue does. And so they can distinguish between these different structures by looking at the absorption of the protons in the hydrogen, which, of course, H2O, water, our bodies are full of water. So a probe field then, it flips the protons from the low energy to the high energy state. Now we know, just like a ball, if you give it a little nudge, will always roll downhill. Things like to be in the lowest energy state they can. And so, in general, the protons in your body will be in the low energy state. And so, when that probe field comes along, and if it's tuned for the energy difference at one particular spot in the body, then it flips it to the higher energy state. It gets absorbed, and therefore we know that in that location there was a proton. Now, different tissues have different concentrations of atoms, specifically hydrogen atoms, and so by seeing the absorption in different places, then they can know, scientists, doctors can know what tissues were present there. And all we need to do is record intensity versus position for the entire body, and we have a three-dimensional detailed image of the interior of a person's body. It's pretty cool.